logarithms and log laws. The goal today is to be able to use the log laws to either expand or compress expressions involving logarithms and to eventually solve equations with logarithms. So here are kind of the three main rules we use for, what do I want to say? That we use to modify logarithmic expressions. So the first one is that the log base b of product x times y, this is equal to the log base b of x plus the log base b of y. People often call this the product rule for logs, although I probably won't say that very often because there is a different just product rule that we learn in calculus. So it gets to be a little confusing if we call both of them product rules. Oh, sorry, this one needs to be admitted. Okay, and then we have this next one, that log base b of x divided by y is equal to the log base b of x minus the log base b of y. In a similar way, we often call this the quotient rule for logarithms. And finally, the third one is that log base b of x to some power is equal to that power a times log base b of x. And that's often referred to as the power rule for logarithms. So let's look at some examples before we do this evaluate. So for this one, do I have enough room? Kind of. Let's go down here. So for this first rule, I like to think of this example that we have log base 2 of 8 plus log base 2 of 4. So log, I did a different example in my notes there. Oh well, this is the one I often think of. So log base 2 of 8, again, we're asking 2 to what power equals 8? That's equal to 3. And log base 2 of 4, that's equal to 2 to what power equals 4? That's going to be 2. And then 3 plus 2 is 5, which you might think, okay, well, that's fine. But I also want to mention that this is the same as, if we were to put these together, we can say, oh, well, that's going to be log base 2 of 8 times 4, which is log base 2 of 32. 2 to what power equals 5? Sorry, 2 to what power equals 32? Oh, that power is 5. So the idea here is that you can combine these together in this way by multiplying the arguments to make it maybe easier to deal with. It even works for things that are maybe not so nice. For example, this is the actual example I want, right? If we had log base 8 of 4 plus log base 8 of 16, well, we could calculate those, right? 8 and 4 both have a similar base. 8 and 16 both have a similar base of 2. We could do some work to actually calculate those. We don't have to. We can combine this, one logarithm, log base 8 of 4 times 16. 4 times 16 is 64. So I get log base 8 of 64. Let me ask all of you, 8 to what power equals 64? Sorry, my volume wasn't on. I'm sure everybody said the answer. Yeah, it's 2. Right, 8 squared equals 64. So this is a way we can calculate something like this. Let me look at one more. Let me show you one more example of how things work here. Specifically, this. So both these other rules. So if you're looking at the quotient rule, again, is that log base b of x over y equals log base b of x minus log base b of y. You can really see it by rewriting it as log base b of x times, I bring this y up, it's y to the negative 1. And then I can write that as log base b of x plus log base b of y to the minus 1. And then I can use the power rule to say, oh, if I've got a logarithm of something to a power, I can bring that power down in front. So this is really log base b of x minus 1 or minus log base b of y. Right, minus 1 times log base b of y, or just minus log base b of y. And then lastly, let me talk about kind of why the power rule works the way it does. If I was going to take log base 2 of, say, 7 squared, I know the power rule, like the power rule says I can just bring that 2 down in front, but here's really why. It's really because, again, because exponentiation, or raising something to a power, is just repeated multiplication. So I can really think of this as log base 2 of 7 times 7. And then I could use the multiplication or product rule for logarithms to write that as log base 2 of 7 plus log base 2 of 7. But then when I add something plus itself again, I just have 2 of those things. So I could say that this is equal to 2 times log base 2 of 7. Whatever that is, right? I don't actually know what log base 2 of 7 is, right? It's some number between 2 and 3. But the point here is just that we can clearly see that this power comes down in front. And it works for any power, right? If I had, log base 2 of 7 cubed, I can do the same sort of thing and say, hey, that's log base 2 of 7 times 7 times 7. And then I can break that up as log base 2 of 7 plus log base 2 of 7 plus log base 2 of 7. And then I have 3 times log base 2 of 7. So those are the logarithmic rules we're going to be using to kind of simplify and solve some other expressions and equations. Let's look at the following. So I know this question's in the notes, but they kind of want, no, actually, let's work on together first. So I want to evaluate the following. So I want to evaluate 1/2 times log base 6 of 81 plus 2 times log base 6 of 2. And the idea, although it isn't spelled out super explicitly here, is that I want to combine this into one logarithmic expression so that I can maybe have a better shot of getting a nicer final result. So to compress multiple logarithms into one logarithm, there's kind of 2 things we have to think of. The first thing is that all of these coefficients need to come up as powers. So I'm going to rewrite this as log base 6 of 81 to the 1/2 power plus log base 6 of 2 to the 2nd power. And I don't think it's too terrible to simplify this part, right? That's just going to be log base 6 of 2 squared is 4. Okay, let me ask you guys, what's 81 to the 1/2 power?
Nine.
Exactly. Or you could also say it's the square root of 81, which is still 9. And then we can combine these by multiplying, right? You're adding 2 logarithms together. You're going to multiply the arguments. This is log base 6 of 9 times 4, which is log base 6 of 36, which is 2, because 6 squared is 36. So this is one example of how we can use logarithms to simplify an expression. So often we use this idea of compressing logarithmic expressions together to solve equations. Can I fit this over here? No, I should use more of the board. So for example, I would like to solve the following. I want to solve the equation log base 5 of x minus 3 plus log base 5 of x plus 1 equal to 1. And so here's what we're going to do. The first thing we're going to do is if we have multiple logarithms added or subtracted together, we're going to combine those into one logarithm. So I'm going to take this left-hand side and rewrite this as the log base 5 of the product of x minus 3 and x plus 1. And here's the thing. I'm trying to solve this equation, but I don't really like, it's weird written as a logarithmic equation. So I'm going to rewrite it. I'm going to rewrite it as an exponential equation. All right, so let me ask you guys. For this exponential equation I'm about to write, what's my base? Yeah, right. And we say it every time we read it, right? It's log base 5 of x minus 3 times x plus 1 equals 1. So my base is 5. What's my exponent? Is it 1 or is it x minus 3 times x plus 1? It is 1. And then it's equal to whatever is left inside the logarithm. It's equal to x minus 3 times x plus 1. Now remind you again, the way I kind of remember this is the logarithm should always be equal to the exponent. So I know that 1 is the exponent and 5 is the base, and it's equal to whatever's inside the log. All right, now I'm just going to try and solve this the way I would usually solve a quadratic. So 5 to the 1 is just 5. And I'm going to multiply this out. I get x squared plus x minus 3x minus 3. Then I'm going to simplify the right-hand side. So I'm going to subtract 5. I'm going to get x squared. X minus 3x is minus 2x. And minus 3 minus 5 is minus 8. And then I'm going to solve this hopefully by factoring, but if not by factoring, then by using the quadratic. So this does factor. It factors as x minus 4 times x plus 2. So we have to be a little extra careful here, but I'm going to ask you guys, what are my solutions? X equal to, and x equal to
4, -2?
Yes, you're exactly right. Well, let me actually backpedal a little bit. You're mostly exactly right. If I were just solving this equation, these would totally be the right answers. However, this is always true when you have a logarithmic equation that you're solving. When you're solving something logarithmic, you have to make sure that your answers are actually in the domain of the original expression. So here's the issue. Logarithms, you can't take a log of something that is 0 or negative. So for any logarithmic equation, you have to have that this stuff is greater than 0. So here, we have to say that x minus 3 is greater than 0, or x is greater than 3. And here, we have to have that x plus 1 is greater than 0, or x is greater than -1. So whatever x values we get, they have to be bigger than both 3 and -1. Now, usually this isn't the way I actually check it, but it's kind of what we're really thinking about. So let me ask you, does 4 satisfy that requirement? Is 4 bigger than 3 and bigger than -1? Yeah, of course. Really, you could just say bigger than 3, because if you're bigger than 3, you're also bigger than -1. So 4 works great. What about -2? Does not work so great, right? -2 isn't bigger than 3 or -1. But if it failed either one, it would be a no-go. So x equals -2 is not a solution here. It's actually called an extraneous solution because it solves some intermediate equation that kind of is the equation we're working with, but not exactly. Something else I want to say here. The way I usually check this, instead of saying x has to be bigger than 3 and x has to be bigger than -1, I just plug in my numbers into my original expression. So if I plug in 4, 4 minus 3 is positive. Great. I can take the log of any positive number. 4 plus 1 is positive. Great. 4 is safe. On the other hand, -2, if I plug in -2 minus 3 is negative. I'm done. We're out. -2 is no good because it made the inside or the argument of the logarithm negative, and we can't take the log of a negative number. I'll point out -2 doesn't work in the original expression, but -2 would totally work here because -2 minus 3 is -5, -2 plus 1 is -1, and -5 times -1 is +5 inside the logarithm. So that's why we're getting -2 as an extraneous solution because it works in a later equation, but not in the original equation. So whenever you're solving logarithmic equations like this, we always have to check to see if our answers are actually really answers of the original expression, which means, and really anything can happen. So you can get however many solutions you have, they can all work, or none of them can work, or some of them can work. So we really have to check each of them. It's not okay to check one and have it not work and then say that the other one has to work automatically. You can have equations that have no solutions, which always feels like a bummer, but it is something that can happen. So let's do this next one. So let's see what we got here. I want to solve again for x. So I've got 2 times log base 3 of x, minus log base 3 of x plus 6, I think. Yeah. Equals 1. I do want to point out that whenever we're solving these logarithmic equations, it's definitely a bummer when you do all that work, you get no answer. Which won't usually happen in these problems, but it could happen, so we have to be aware of it. One thing I want to point out is that whenever you're working on a logarithmic equation, you're always going to have the same base, right? You can't really deal with logarithmic equations where you have a base 4 and a base 5 or different bases. Like, it's just not something that's done. So don't worry about the bases possibly being different. So before I can combine these logarithms together, we have to get rid of the coefficient for each of them. So this 2 is causing a problem. I can't really put a logarithm with a different coefficient here. Right here, the two coefficients 2. Here it's 1 or -1, depending on how you want to think about it. But I'm going to rewrite this as log base 3 of x squared. I'm going to bring that 2 up as the power. Minus log base 3 of x plus 6 to 1. And then I'm going to combine these two logarithms into one logarithm using the quotient rule for logarithms. So I'm going to write this as log base 3 of x squared over x plus 6 equal to 1. All right, this next step is the step I often see people forget. I have definitely seen many, many people in the past say x squared over x plus 6 equals 1, which is not true, right? We don't want this to equal 1. We want this to equal 3 because 3 to the 1 equals 3. So really what I'm saying is I should rewrite this as an exponential equation. My base is 3, my power is 1, and it's equal to the inside stuff. So then, solving this one isn't quadratic yet. I have to multiply both sides by the denominator. So I'm going to rewrite this as 3 to the first is just 3, times x plus 6 equals x squared. So this becomes 3x plus 18 equals x squared. And I would bring everything to the right-hand side because I like my highest power to have a positive coefficient. So I'm going to write this as 0 equal to x squared minus 3x minus 18. You could certainly write it as negative x squared plus 3x plus 18 equals 0, but I think it's harder to factor it that way, so I'm going to write it this way. So then I'm going to factor it. I'm going to get x minus 6 times x plus 3. Is that right? Let me double check. I plug in, let's see if I, yeah, add negative 3. Yeah, that works. So I'm going to say now, what are my possible solutions? X could equal what? Or x could equal what? What about from this factor? How from over here?
Negative 3.
Thanks. Okay, now we're going to look at these, and we're always going to go back to the very original first equation we started with. So let's look at x equals 6. I plug in 6 here. Is the inside positive? Yeah. How about I plug in 6 here? Yeah. So 6 is good to go. All right. What about negative 3? So before you say anything, if I plug in negative 3 here, is it okay?
Yes.
Yeah, negative 3 is perfectly fine here. If I plug in negative 3 here, it's not, right? You're taking the log of a negative. So since it doesn't work in one of the spots, negative 3 is no good. So our only solution here is x equal to 6. I do want to mention again, even though both of these examples had one solution that worked and one solution that didn't, you can have examples where both solutions work or neither solution work, or you could even have more than 2 solutions. Yeah. Let's look at one more example that I don't think I actually have on the notes, but thought was worthwhile. So let me take a look now, because it's a little bit different here. One sec. Yeah, I definitely want to do another one. Cool. All right, so let's look at this next example. That's my own. Let's try to solve. In fact, so I think I'm going to have you guys work on this one for just a minute, and I'm going to wait here silently. So here's the equation I want you guys to try and solve. Log base 2 of x plus log base 2 of x plus 7 equals 3. So there are 2 steps you should take. The first step should be to combine it. The second step should be to rewrite it as an exponential equation. And then you should have to factor some sort of quadratic. And I'm going to I'll give you 2 minutes to work on that. Might not be quite enough time, but it's enough time to get through most of it. this time. Okay, so hopefully you ended up getting that, I think, 1 was a solution and -8 was an extraneous solution. Well, let's take a look and see. I'm going to combine these together. I'm going to get log base 2 of x times x plus 7 equal to 3. And I'm going to rewrite this as an exponential equation. My base is 2, my power is 3, and it's equal to the argument there, which is x times x plus 7. Simplifying, 2 to the third is 8. X times x plus 7 is x squared plus 7x. Bring the 8 over is -8, so 0 equals x squared plus 7x minus 8. And then factor. That factors as x plus 8 times x minus 1. So my possible solutions are x equal to -8 and x equal to +1. And here we see that -8's an extraneous solution because if you plug in -8, either one of those is negative. Whereas x equal to 1 is an okay solution. If you plug in 1, that's positive and that's positive. I also want to mention, although our examples, we've seen that the negative number is not a solution. So here's one you can work on your own at some point that we're not going to do right now. But I will tell you that this equation, log base 3 of 7 minus x plus log base 3 of 1 minus x equal to 3. This has x equal to -2 as a solution. I think you should do that problem on your own when you have a chance, but I really want to emphasize here. It's okay if x is negative, it's just that the argument can be negative. So -2 is perfectly fine here because 7 minus -2 is positive and 1 minus -2 is also positive. So you should do this problem on your own when you have a chance. It's a good problem. Okay, moving on to some other things we can do with logarithms. Let's see. So I want to solve for x, and these are going to be, so these are going to feel kind of funky, I feel like. So I'm going to solve for x, where my equation is 8 to the x equals 32. And depending on what we've got going on, you can get a nice solution or a less nice solution. And kind of the deciding factor is if your numbers on either side have a common base. If they do, we can typically get a nice fractional solution or rational solution. If they don't have a common base, we're usually left with leaving something in terms of a log. So here, sorry, I wrote the wrong, I skipped a step. I apologize. I meant to start with this. Log base 8 of 32 equals x. Sorry. Which then we can rewrite as this exponential equation. And I should say it again. If my base, which is 8, and my argument, which is 32, if those have a common base, which these do, the common base is 2, then we can usually find a nice solution. We'll see in the next example that we won't be able to. So here I can rewrite both sides as powers of 2. 8 is 2 to the third, and that's still to the x. 32 is 2 to the fifth. I can re-express the left-hand side by multiplying the powers. 2 to the third to the x is 2 to the 3x. And 2 to the fifth is still 2 to the fifth. And then the only way for 2 to the something to equal 2 to the something else is for these somethings to be the same. Right? 2 to the fifth is only equal to 2 to the fifth. So 3x has to equal 5. So x has to equal 5 thirds. You can go back and check, oh yeah, if I plug in 5 thirds, 2 to the 3 times 5/3 is 2 to the 5th. So 2 to the 5th equals 2 to the 5th. This equation, this question, there's no worry about an extraneous solution because there isn't any variable in our logarithm. So you only have to worry about extraneous solutions if you're taking the log of something that might end up being negative. Here, the insides are always positive because it's just 32, so there's no concern. Okay. And now we're going to move on to some other equations which are going to have less satisfying answers. For example, what if I wanted to solve 10 to the x equals 2 or 3 to the x equals 4? So for 10 to the x equals 2, I'm going to rewrite it as a logarithm. I can rewrite it as log base 10 of 2 equals x. Right? 10 and 2 don't have a common base. They're not both powers of the same number. And that's kind of it. This is my solution. It doesn't feel very great, but it is. The only thing I will say here is that specifically for log base 10, since it's such a common base, we do just write it as log. So I should actually write my answer as x equal to log of 2. And that is my exact answer. Now, if someone said, solve this equation, this is the answer I would expect. If someone said, give me a decimal approximation of the solution to this equation, then we would use a calculator. So, or another example is like if maybe x is representing something like the age of a thing or the number of days it's been since something or the amount of stuff, then it might make more sense to actually give a decimal approximation. But if someone asks for an exact answer, you should just leave it like this. I will tell you the decimal approximation is about 0.30. So this is approximately 0.30. Again, this is the answer we're looking for. We can do the same thing here. 3 and 4 don't share a base. So I could re-express this as log base 3 of 4 is equal to x. And that would be my solution. Now, there is an issue here. And the issue here is that if I wanted a decimal approximation, a lot of calculators don't have a log base 3 button or a log base 4 or anything but log base 10 and log base e. So another different way to solve this equation is the following. You take either the log base 10 or the log base e of both sides. Most teachers, most students usually prefer the log base e because it's got less letters to write. So you could do either the log base 10 of 3 to the x equal to the log base 10 of 4. I'm not writing the base because we usually don't for that. Or I could do the log base e of 3 to the x equal to the log base e of 4. Either way, we're going to get to the right thing. I typically write this because I am lazy and it has one less letter to write. I know it feels like a silly reason to do it, but. So then we're going to solve for x. And the way we're going to solve for x is we're going to use the power rule and bring that x down in front. So that x times the natural log of 3 is equal to the natural log of 4. And then we're just going to divide both sides by the natural log of 3. That pen doesn't look great. That's much better. So we end up getting x on the left, and we get the natural log of 4 divided by the natural log of 3. If you use log base 10 instead, you would get x equal to the log base 10 of 4 over the log base 10 of 3. And you can check on your own if you want that if you plug this into a calculator or you plug this into a calculator, they're going to be the same. Just kind of neat. Okay. One more example of this nature. So if your base is 10, it obviously makes sense to use log base 10. In a similar way, if your base is e, it makes sense to use log base e. So if I was trying to solve e to the x equal to, this one's actually going to be a little more complicated, 10 to the x plus 1. I actually suppose in this example, you would be justifiably correct using either the natural log or the log base 10, since you have a base of e and a base of 10. I'm going to use the natural log because that's usually the choice people make. So this is going to be kind of weird. One way you could do this is you could say, I'm going to rewrite this as an exponential equation. So I could say log base e of this equals x. Right, that is the same equation, e to the x equals 10 to the x plus 1. This is not what people usually do. Right, and I should say this would be a natural log of 10 to the x plus 1. Here's what people usually do when these exponential equations start getting more complicated. They just take the natural log, or sometimes log base 10, of both sides of the equation. So instead of doing this, although this is fine, we do this. I'm going to take the natural log of e to the x equal to the natural log of 10 to the x plus 1. I really, really, really want to emphasize here, we are not multiplying both sides of a natural log. Just like you wouldn't multiply both sides by a square root, right? If I was trying to solve x squared equal to 9, and I do this, it's not that I'm multiplying by a square root, I'm taking the square root of both sides. I'm doing the same thing here, I'm taking the natural logarithm of both sides. So the natural log of e to the x is just x, right? Because again, natural log is really log base e. Sorry. And here we're saying e to what power equals e to the x? Oh, it's got to be x, because e to the x equals e to the x. So x equals the natural log of 10 to the x plus 1. Ooh, that's not good though. I can't have an x in my solution for what x is. That's a problem. So when I'm trying to solve for x, I have to get x equal to just a number without any variables in it. So I'm going to bring this x plus 1 down in front as a power. The power is going to come in front as a coefficient. So x equals x plus 1 times the natural log of 10. And I'm going to distribute that natural log of 10 to each of those terms. That's my bad. Throw this away. So I have x equal to x times natural log of 10 plus 1 times natural log of 10. And now I'm going to group all my x's on one side and solve for x. So bring this over to the left. Oh, by the way, I will point out, right here, the equation is the same as right here. So either way, we would have gotten to the same place, whichever way you want to think about it. So bring this over to the other side. So x minus x times natural log of 10 equals natural log of 10. Factor out an x. You got x times 1 minus natural log of 10 equals the natural log of 10. And then finally divide by what's multiplying x here. So that x is equal to this natural log of 10 divided by this 1 minus natural log of 10. And that is about as simple as it gets without using a calculator. So this would be our final answer. If you wanted to use a calculator, it would be approximately negative 1.77. I really want to stress, if someone asks for an exact answer, they mean this, not this decimal approximation, right? Because this isn't, negative 1.77 isn't exactly the answer, right? It goes on and on and on forever and ever and ever. So exact answer, approximation. All right, what do we have left to see? Oh yeah, okay. A couple more equations like this. Cool. Yeah, all right. How much time have we got? Yeah, I got enough time. So let me do that. Yeah, let me do that on that. Things get a little bit uglier if the bases aren't E or 10, but not really that much uglier. So, oh, sorry, we got this problem first. So we got number 4, it'll be 5 and 6. So 4 is log base x of 27 equals -3/2. And so of course, especially when I'm trying to solve for the base, which is kind of weird, I'm definitely going to rewrite this as an exponential. X to the -3/2 equals 27. All right, and now what do I have to do to both sides of this equation to isolate x? What power should I raise both sides to get x all by itself with just a first power? Any brave volunteers?
-2/3?
Exactly. Or more generally, the reciprocal of that. But yes, exactly -2/3. But if we do it to this side, we have to do it to that side. So here we get x to the first, because -3/2 times -2/3 is -6 over -6, which is 1. And here we get 27 to the -2/3, which I'm going to write as 27 to the 1/3 to the -2. Because 27 to the 1/3 is the cube root of 27, which is 3, still to the -2nd. 3 to the -2nd is 1 over 3 squared, and that's going to be 1/9. Which is kind of a weird base, right? Most of our bases, when we talk about logarithms, most bases are either nice positive integers, like 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., or the number e. Those are, like, you can have fractional integers. It is certainly plausible for 1/9 to be a base. Sorry, I said integers. You can have a base of 1/9 or 1/2 or other weird fractions. But really, for the most part, in your mathematical lives and in mine, you only ever really see logarithms where the base is like 7 or 8 or 1,000, or e is the only non-integer number you typically see. Not that you can't see other ones, but we don't usually. All right, let's do number 5 here on this, which is solving 5 to the 2x minus 3 equal to 4. And although, so again, I want to point out, there are really kind of 2 ways you can go about this. You could rewrite this completely as log base 5 of 4 equals 2x minus 3. But the usual, more standard way of solving an equation like this is to take the natural log of both sides. And again, the reason there isn't because there's an e showing up, because there isn't. It's because the natural log is a button that we have available on our calculator. That's really the reason why. It's because natural log is something you can actually find an approximation of on our calculator really easily. Whereas log base 5, at least on my calculator, nope, I don't have a log base 5 button. Or even a log base, whatever, pick your base. So we're going to do the natural log of 5 to the 2x minus 3 equal to the natural log of 4. And then we're going to bring down the power. So this 2x minus 3, I'm going to write as 2x minus 3 parentheses times natural log of 5 equals natural log of 4. And then we're going to solve for x. And there's a couple different schools of thought here. Some people prefer to divide by natural log of 5 first. That is not what I prefer to do, but you can do that if you want. You can totally divide by natural log of 5 and then add 3 and then divide the whole thing by 2. That is perfectly legitimate. The way I usually like to do it instead is I like to distribute. So I'm going to distribute this to each of these terms here. So I'm going to have 2x times natural log of 5 minus 3 times natural log of 5 equal to natural log of 4. And then I'm going to isolate the x term. So this is the only thing with x in it. So I'm going to add this over to the other side. So 2x natural log of 5 equals natural log of 4 plus 3 natural log of 5. And then lastly, we're going to divide by the coefficients of x. So I'm going to divide everything by 2 natural log of 5 and get x equal to natural log of 4 plus 3 natural log of 5 divided by 2 natural log of 5. And that's how I would leave my answer. And yeah, I think we have time for the last one, which is good. We have more than 2 minutes, which is definitely enough time to do one more problem. All right, so here's the last one on the notes. It is 3 to the x plus 1 equals 5 to the 2x. And I want to point out, this one is a little more complicated because both sides have a variable in their exponent, whereas in the previous equation, only one side had a variable in the exponent. So there's going to be a little more algebra to work with here. Even with that said, we're still going to start by taking the natural log of both sides. So the natural log of 3 to the x plus 1 equals to the natural log of 5 to the 2x. Now, the reason we take a logarithm of both sides of an equation is because a logarithm allows us to pull a variable out of the exponent into just like the regular place where everything lives. So we get to say this x plus 1 can come down in front, this 2x can come down in front. So we have x plus 1 in parentheses times natural log of 3 equal to 2x times natural log of 5. I didn't put the 2x in parentheses because there isn't like more than one term, although you certainly could. You just don't have to. So here we have to distribute this natural log of 3 to each of the terms that are added together here. You do not have to do that here, right? Natural log of 5 times 2x is just natural log of 5 times 2x. So here I get x times natural log of 3 plus 1 times natural log of 3 equal to 2x times natural log of 5. And now I want to group all the things that have x on one side. So I want all the x terms to be on the same side and all the not x terms to be on the other side. So since I already have an x term over here and nothing else, and I have the not x terms over here, I'm going to bring all my x terms to the right. So I'm going to write this as the natural log of 3 equals 2x times natural log of 5 minus x times natural log of 3. And then, and this is an additional step compared to the last problem, we have to factor out an x from the side that all the x's are on. So I'm going to rewrite this as natural log of 3 equal to, we'll factor out the x, and be left with 2 times natural log of 5 minus natural log of 3. I divided out the x from each of those. And lastly, we're going to isolate x by dividing by all of this. So that x equals the natural log of 3 divided by 2 natural log of 5 minus natural log of 3. And that's that. And that's 1 minute after I should have ended, so I should stop. All right.